Module 5 Design Methodology. A design methodology codifies the process of design, verification, and preparation for manufacture of a product. It involves development of virtual prototypes to support design analysis and refinement. In this module, design and verification ideas are elaborated, and also the larger context in which digital systems are designed is considered. Design flow. Design methodology is not standardized across the industry. Each organization defines its own design methodology based on the kinds of the design projects it undertakes and evolves the methodology from project to project. A prototypical design methodology divides the design flow into a number of stages, that is functional design, synthesis and physical design. Each stage includes verification steps to ensure that the design meets its requirements and satisfies constraints. Figure shows the elements of the design flow, including hierarchical hardware-software co-design integrated into a single diagram. The product of the design process is a set of data files used in manufacturing the product. Each manufactured unit is then tested and delivered to the end customer or market. The design flow for embedded systems is refined to include design and verification of the embedded software. For many complex systems, the hardware is simply the platform upon which to deliver the software. Developing the software is a major portion of the system development effort. A key part of a design methodology is the set of electronic design automation tools used to support it. EDA tools can analyze and refine virtual prototypes. Architecture exploration. Architecture exploration is the process of modeling and evaluating candidate designs at a high level of abstraction. A system is partitioned for subsequent refinement. Logical partitioning identifies functional components, whereas physical partitioning identifies physical hardware components. Logical functions are mapped onto physical partitions. The physical partitions can include processor cores, accelerators, memories, and I/O controllers. Hardware-software partitioning involves a given logical component may be mapped to a specialized hardware component whose only task is to implement the logical component. Another logical component may be mapped to a software task run on a processor core under control of a real-time operating system. Example: system partitioning, a transport monitoring system. Consider a road transport monitoring system that checks whether freight trucks drive from one part of the country to another in too short an interval. Stations on freeways each have a video camera on a gantry road. The video images are analyzed to identify the license plate of each truck passing underneath, and the time and the license number are logged. The information is transmitted to a central facility for recording and comparison with information from other stations. A hypothetical functional decomposition, that is logical partitioning of the monitoring station, is shown in the top figure. It includes logical components for input of video from a camera, filtering to remove noise, edge detection, shape detection, license plate detection, character recognition to identify the license plate, logging, network interface, system control, and diagnostic and maintenance tasks. This logical structure can be mapped onto the functional structure, that is physical partitioning, shown at the bottom of the figure. In this case, the physical components comprise an embedded system with accelerators for video processing up to the shape detection stage. License plate detection and recognition, logging, system control, and diagnostics and maintenance tasks are mapped onto software tasks running on the processor core. Architecture exploration and partitioning is often done by expert system designers. Very difficult to automate these tasks using EDA tools. The result of architecture exploration is a high-level specification of the system. For each of the components in the system, specification describes the function, connections to other components, and constraints. The specification might be expressed in a language that can be executed or simulated, such as certain forms of unified modeling language. Functional design. Functional design refines partitions to a level from which implementations can be synthesized. A behavioral model of the component is developed, expressing its functionality at an intermediate level of abstraction between system level and register transfer level. The components may be implemented through IP reuse or by core generators. IP or intellectual property refer to reusable components from a previous system, from a library of components, or from a component vendor. A core generator is an EDA tool that generates a model of a component based on parameters that describe its function. Need for revision management. Revision management is required in hardware model development and software development. Revision management software helps coordinate designers' work by maintaining a repository of versions of the code. It is included in EDA tool suites or open source tools. Functional verification. Functional verification ensures that the refined design meets functional requirements and can be performed using simulation and formal verification. Functional coverage is the proportion of functionality verified. Successful verification of a system requires a verification plan that identifies number 1, what parts of the design to verify, number 2, what functionality to verify, number 3, how to verify. Hierarchical decomposition of the system identifies what parts to verify. The specification of each component defines what functionality to verify. At higher levels of design hierarchy, it is much harder to verify functional requirements under all circumstances. Use functional coverage. Use techniques like directed testing and constraint random testing to find out how to verify. Directed testing involves identifying particular test cases to apply to the DUV and checking the output for each test case. This is effective for simpler components. Constraint random testing involves a test case generator randomly generating input data subject to constraints on the ranges of values allowed for the inputs. Example verification languages are Vera-E system Verilog. Both techniques require checkers that ensure that the DUV produces the correct outputs for each applied test case. A comparison test bench is shown in figure. It verifies that the implementation has the same functionality as the behavioral model. Directed and constrained random testing are both simulation-based verification techniques. They are not feasible to attain. It is not possible to attain 100% coverage. Formal verification allows complete verification that a component meets a specification. The specification is embodied in one or more asserted properties expressed in a property specification language such as PSL. A property can be as simple as a Boolean expression relating the values of signals in the design. A formal verification tool performs state space exploration to verify the asserted properties. Writing properties that completely and accurately capture the intent of a specification is very difficult. Properties can also be used in simulation-based verification of a system to generate a checker. Properties can be reused for formal verification after an initial phase of simulation-based verification. Hardware-software co-verification. Hardware-software co-verification uses instruction set simulators and hardware emulation to test software between hardware models or before hardware models are available. Software and hardware can be tested together using a co-simulation. Synthesis. Synthesis is the refinement of functional design to a gate-level netlist. Synthesis can be performed automatically using an RTL synthesis tool. Automatic RTL synthesis is used for FPGA-based designs. Custom design is required if a design is complex, has very high performance requirements, and is implemented as an ASIC. RTL synthesis starts with the models of the design refined to the register transfer level. Many VHDL or Verilog features cannot be synthesized into equivalent gate-level circuits. RTL synthesis tools require that RTL models be written using a subset of language features. Example, sequential hardware should be expressed using always blocks. Early synthesis tools performed relatively simple pattern recognition on HDL source code to determine which hardware circuits were implied. Subsequent developments in synthesis tools focused more on improving the quality and optimization of the synthesized hardware. RTL models cannot be portable across a range of tools. To help designers write interoperable models, the IEEE had defined two standard coding styles for synthesizable models. One for VHDL IEEE standard 1076.6 and other for Verilog IEEE standard 1364.1. A synthesis tool starts by analyzing the model, checking to make sure the code conforms to its style requirements. It also performs some design rule checks such as checking for unconnected outputs, undriven inputs, and multiple drivers on non-resolved signals. The tool then infers hardware constructs for the model. This involves things like analyzing wire and variable declarations to determine the encoding and the number of bits required to represent the data, analyzing the expressions and assignments to identify combinational circuit elements such as adders and multiplexers, and to identify the input, output, and intermediate signal connections, analyzing always blocks to identify the clock and control signals, and to select the appropriate kinds of flip-flops and registers to use. The tool determines an implementation each of the inferred hardware elements using primitive gate elements selected from a technology library. Technology library is a collection of components that are available within the implementation fabric selected for the design, provided by ASIC or FPGA vendor. Typical components in a library are inverting, non-inverting gates, small multiplexers, carry chain components, and flip-flops. The process of translating the design into a circuit of library components is guided by synthesis constraints. Such constraints include bounds of clock periods and propagation delays. Synthesis tool uses the constraints to choose among alternative implementations. Directly instantiate specific predetermined implementations created using the core generators. Verify whether the implementation of the synthesis tool meets timing constraints. Simulate the implemented design to ensure that it meets functional requirements. Physical design. Physical design refines the gate level design into an arrangement of circuit elements in an ASIC, or builds the programming file that configures each element in an FPGA. Physical design of ASICs. Physical design of ASICs consists of floor planning, placement, and routing. Floor planning. Floor planning involves deciding where each of the blocks in the partition design is to be located on the chip. A number of factors influence the floor plan. The first one is blocks that have large number of connections between them should be placed near each other. Second one, blocks that are connected to external pins should be placed near the edge of the chip. Number 3, the blocks should be arranged to make the chip as close to square as possible, since that influences the size of the package that can be used. Square chips are easier to package than rectangular chips. Floor plan involves arrangement of power supply and ground pins and internal connections. The connection and distribution of clock across the chip, provision of channels for laying out interconnections between blocks. EDA tools can assist to visualize floor plans and rearrange blocks, ensuring all the time that a floor plan is feasible, and by analyzing alternative floor plans to determine figures of merit. Placement and routing. Placement and routing involves positioning each cell in a synthesized design and finding a path for each connection. The main goals are to position all cells and route all connections while minimizing area and delay of critical signals. The result of placement and routing is a suite of files to send to the chip foundry for fabrication. Detailed timing information is generated based on the actual position of components and wires. Detailed timing simulation is a final check to ensure design meets its timing constraints. Placement and routing are automated by EDA tools. Physical design for FPGAs. Physical designs for FPGAs involves deciding how to implement the synthesized design using the programmable resources of a prefabricated chip. This involves floor planning, mapping, and placement and routing. Floor planning. A good arrangement of blocks in FPGA fabric reduces the number of long-distance interconnects, simplifies connections to I/O blocks and their associated pins. For smaller FPGA-based applications, the floor plan generated automatically by the vendor's EDA tools is sufficient. For larger designs, if there is difficulty in fitting a design into a given FPGA, either attempt to improve the floor plan or use a larger FPGA. Mapping. Mapping involves identifying the FPGA specific resources to be used for each of the library components instantiated in the synthesized design. The result is an implementation of the design using logic blocks, I/O blocks, and FPGA specific resources as opposite to the library cells used by the synthesis tool. Placement and routing. Placement and routing involves identifying specific blocks and routing wires in the FPGA to use for the mapped blocks while minimizing area and delay for critical signals. This is performed by automatic tools, that is EDA tools provided by the FPGA vendor. EDA tools constraints on placement and timing can be specified to improve placement or routing. The final result is a bit file specifying how the FPGA is to be configured. Detailed timing information for the design can be generated based on the internal parameters of the logic blocks and interconnect in the FPGA. Final timing simulations are performed to verify that the implemented design meets the timing constraints.